Welcome to Wireless LAN Weekly, a podcast focused on the wireless networking professional. We aim to educate, inform, entertain, and inspire. Get ready to listen and enjoy. Now to our host of the show, Keith Parsons.
Hello again, this is Keith Parsons with WirelessLANProfessionals.com, and this is episode number 2 of Wireless LAN Weekly. In today's show, we have some information on client arbitration, of course some interesting facts, rants, and other little elevator speeches that we always throw in. And our final segment today will be Adam Conway talking about management, control, and data planes. Thanks for coming and listening in, and now on to the show.
Today's wireless networking definition from the CWNP Dictionary of Wireless Terms and Acronyms.
This is Joel Barrett, and today's term is on modulation. Modulation is any of the several techniques for combining user information with a transmitter's carrier signal by changing one or more properties of the signal. There are several types of modulation that are used in regards to Wi-Fi. For example, DSS OFDM is a direct sequence spread spectrum orthogonal frequency division multiplexing. Obviously, you can tell that some of these modulation types get a little confusing, but they are the underlying parts of Wi-Fi that make things work. So if it wasn't for the modulation, you wouldn't be able to decode that into packets and bits and bytes like you need to see on the IP side of the network. So this is Joel Barrett for the CWNP Dictionary, and tune in again for the CWNP Dictionary Term of the Day.
Rant, pet peeve, what really bugs you? 60 seconds of complaining starts now.
Hello again, this is Keith Parsons. Another thing that really bugs me is the use of dB as the sole measurement of whether or not a wireless network is going to work. Yes, we have to have dB. dB is to wireless what connectivity is to wired. When we're pulling Cat5 cable, the connectivity, meaning the copper can carry electricity from end to end, is critical. You must have it. In wireless, dB, or receive signal strength indicator, that you have RF energy at the client site, is also critical, but is not sufficient. Connectivity is not sufficient for wired, and dB alone is not sufficient for wireless. We need to make those other measurements. Just like in Category 5 cable, we have to measure near side crosstalk, far side crosstalk, pinouts, twist ratios. In wireless, we have to measure not only coverage, but overlapping coverage or double coverage. We also need to measure channel interference to see how large our collision domains are, as well as data rate, throughput, noise floor, and user density. So let's stop looking at the world only through the eyes of dB and look at all the statistics that we need to measure so we can make our wireless networks go as well as they can.
Things every wireless LAN professional needs to know. Gear up, buckle down, and stand by for the real techie stuff.
Today, I'm proud to announce Marcus Burton, Director of Product Development for the CWNP Program, will be talking to us on client arbitration. He's written a great white paper. I strongly encourage you to go to the CWNP website and download that white paper. Marcus?
Thanks, Keith. I took on the process and the project of drafting what are the mechanisms used by clients and APs as well to access the channel, the wireless medium, in the 802.11 specification. So a creative title to my white paper, 802.11 Arbitration. I just like to keep it nice and simple. So the process took me a few months actually to just kind of sift and sort through the 802.11, mostly -2007 specification, and just look at the details of how in the world does this work, what are the processes, what are the steps, what are some of the real nitty-gritty details, and why is it important. So that's what the paper is about. The reasons that I wanted to write this paper, my primary motivation, there's really a few different reasons. G.T. Hill, if you've heard his name, he is so motivated teaching 2.11 arbitration. So once I had a chance to sit in his class and listen to his lesson on arbitration, the passion for that topic just sort of caught fire for me. The importance of it when you're planning a network and network design, and even just understanding the background of how it works, just just really kind of made sense for me to want to know this in detail. And when I first heard it from GT, I didn't know the details very well. So that was my own sort of personal motivation to want to really learn the topic well. And then since there's really not a lot of published material on the topic out there, I wanted to just put it in, hopefully an easy to understand format. I think it's like a 24-page paper of technical details, but hopefully quite a bit easy to understand than the 802.11's, which sometimes just need to understand. So those were sort of my motivating factors. Why would you even want to read it in the first place? There's really a few reasons that stand out to me. Like I said before, network design, understanding how 802.11 devices even contend for the medium helps sort of form a comprehensive design approach, especially as it relates to things like capacity planning, network utilization, those sorts of things. Of course, QoS is a major topic when it comes to arbitration. When you're supporting, you have a multi-service network supporting latency-sensitive applications, applications that have stringent demands like that. It's just so important to make sure your network is designed properly, and some of the settings that you have configured on your network, it's just important to understand how they all interact. Plus, it's good to even just know how is priority even provided to different devices that need higher priority, like voice over Wi-Fi, or if you're supporting video over Wi-Fi. The other thing that's important is, especially with 802.11n's, 5 specific access parameters, basically. So if you have 802.11a and 802.11g, or 802.11n mixed in with either of those 2 5s, which one takes priority? Is there any priority? Is what the 802.11 specification specifies for priority, is that enough even to, to make your network operate smoothly? What are even some of the shortcomings of 802.11 arbitration as it's defined by the 802.11 standard? And this is, I think, especially important as it relates to airtime fairness with 802.11n. There's really not enough 5-specific priority provided by the standard. So a lot of these proprietary mechanisms with airtime fairness have come out as well. So arbitration as a whole, as a topic, is sort of fundamental to all of those different things. And so understanding arbitration, how it works, just sort of prepares you to be able to do those things, to design a network with QoS support and to decide on features like airtime fairness. So some of the highlights of the paper, just going through some of the major points throughout the paper, just to bring that up here. Sort of start the paper in the topic of arbitration with an analogy, and I'm not generally an instructor type. I don't stand in front of classes giving analogies for technologies and how they relate to everyday life, but there is a really easy analogy that comes along with 802.11 arbitration, and that is social interaction, how we wait for one another to speak. When we're in group settings, if someone else is talking, we don't jump in on top of them and start talking at the same time, because then no one understands what either of us are saying. So there's some protocol that's involved in how we interact, who talks when, who doesn't talk when, how we listen to one another. If 2 people start talking at the same time, you realize that there's a problem, you stop talking, and you wait sort of a random time to start talking again. So there's a protocol analogy there with social propriety. And that's all required because just like conversation in the medium that we use to interact with one another, the wireless medium used for 802.11 wireless is half duplex, which means that only one device can really effectively be talking at a time. So you've got to coordinate between different devices to say who talks when. So one of the basics relating to that is the MAC channel access architecture. This is specified in the 802.11 standard. So distributed coordination function, which is DCF, is the acronym for that, is the basic building block. It's the mandatory channel access method to be supported in a BSS. And then the other ones, there are 3 optional methods. There's PCF, which is point coordination function, which is it's not a contention-based, it's a contention-free mechanism. So AP basically polls different devices that are part of the PCF, and it says, Do you want to transmit something now? Do you want to transmit something now? So it polls instead of using contention. And there's a hybrid coordination function, which there are two subtypes of that. There's EDCA, which is Enhanced Distributed Channel Access, and there's HCCA or HICA, hybrid or HCF Channel Coordination Access. So if I got all those acronyms right, I'll be amazed. But there's plenty of acronyms to go around. But those two are also both optional, and those are both the two required methods to support QoS. So EDCA is a contention-based QoS mechanism, and HICA, HCCA, is contention-free. It's basically the PCF with QoS support. So PCF and HICA, both the contention-free methods, neither of those are used. So now that I've introduced them, you pretty much forget about them. So the basic channel access method for 802.11 networks is, or the protocol rather, not method, is CSMA-CA, Carrier Sense Multiple Access with Collision Avoidance. And for anyone who has a wired background, you might realize that that's different from wired networks, which uses collision detection. Since wireless transmitters can't detect a collision on the air interface, they basically have to infer one by not receiving an acknowledgement frame. So CSMA-CA, as it works in wireless, is really designed to try to minimize collisions. You can't prevent them, you can only minimize them. So the channel access methods, there are specific mechanisms that are used to try to minimize collisions. So the first one is carrier sense, of which there are two subtypes. There's physical carrier sense, which is CCA, clear channel assessment, and that's basically the physical detection of someone else transmitting. Is someone else transmitting, and you can detect it physically. So there's an energy detect mechanism with that. That's basically raw RF noise. If it reaches a certain threshold, you know someone else is transmitting. And then there's a carrier sense portion of that, and that is preamble detection. So if you receive the PHY preamble of someone else's frame, then you know that someone else is transmitting, and that actually has a certain power or energy RF threshold as well. So carrier sense has two subtypes, physical and virtual, which I'll talk about next. Physical carrier sense has two subtypes, energy detect and carrier sense, or preamble detection. So virtual carrier sense is not quite like physical carrier sense. Virtual carrier sense actually uses the duration values in the MAC frames. So a MAC frame at layer 2, in the header, there's a duration field, which specifies the length of the upcoming frames. So a station receives the duration value, processes it, sets a NAV timer, that's network allocation vector timer, and basically counts down that value. So once that value reaches 0, and frame transmission sequence is done, and then it realizes that the medium is idle again, so it can go back to contending. So carrier sense, that was the first mechanism. The next mechanism is the interframe space. So after someone successfully transmits a frame, the communication is done, is completed, and your station would like to transmit a frame. It has to observe an interframe space, which is an idle period between transmissions, basically. And the whole purpose of interframe spacing is to buffer between two frames to minimize collisions. And then it's also a way, there are different interframe spaces, so it's granular control for which types of devices access the medium when, which frames can be transmitted when, and which access categories within a device can access the medium and when. So the 5 different types of interframe space are the CIFs, the DIFs, the AIFs, that's AIFS, the EIFs, or I'm not exactly sure how everyone pronounces that, but that's how I pronounce it, the EIFs, and that's EIFS, and then there's a RIFs, RIFS. So I'm not going to go into the details of each of those, but you can read the paper if you want to know what each of those, how they relate and how they work. So the next mechanism is the contention window and the random back-off timer. So in order to create a certain amount of random access to the wireless medium to minimize collisions, again, stations have basically a contention window. So it might be from 0 to 31, or it might be from 0 to 5, or it might be from 0 to 7. So basically they have this window of numbers that they can choose. It's a randomization process. So they choose a number, and then they have to wait that number of slots before they can transmit a frame. Okay, so the contention window and the random back-off process, it's all based on statistical likelihood. So a device has a contention window of, let's just say, for example, 0 through 31. And then another device has a contention window of, let's say, 0 through 15. So the device with 0 through 15 has a statistical likelihood of selecting a lower number, or has a greater statistical likelihood of selecting a lower number than the device that has 0 through 31. So the device with 0 through 31 could still select a lower number. They might select 3, whereas the other one might select 12. So it's all based on statistical likelihood, giving it a smaller or a larger window of random numbers from which to choose to perform back-off. So this back-off, just to elaborate a little bit more, is the counting down of slots. So a slot is a fixed amount of time for a specific PHY. So it might be 9 microseconds, or it might be 20 microseconds. And so let's say a device has a contention window of 31, 0 to 31, and it picks 17 as the number that it happens to randomly choose. It has to wait 17 slots, 17 instances of a slot time. So let's say the slot is 9 microseconds. So that device has to wait that number of 9 microseconds. So if it picks the number 15, it has to wait 15 instances of 9 microseconds. So 15 times 9 microseconds, whatever that math is. It has to wait that long at least before it can transmit a frame. So while it's waiting, at the end of each 9 microseconds before it decrements the random back-off timer, it's detecting the wireless medium to determine if there's any RF noise, if there's another device transmitting. So if someone else transmits while that device is waiting, then it has to basically stop. It observes the other person's transmission, quietly waits, and then once that transmission is done, it waits its interframe space, and then it begins decrementing again. So when the slot time or the random back-off timer finally reaches 0, then it can finally transmit a frame. So those are the basic mechanisms. I realize that contention window and random back-off timer is it's a little bit more difficult to understand just by listening. So visual references are usually pretty helpful, which is why in the paper that I wrote, I provided several graphics, showed some beacon frames even, and showed some charts and tables that show how these different mechanisms work, how to calculate them, how to understand how long one device is going to wait versus another device. So there's a lot of good visual aids there that even if you're not going to memorize all this stuff, it's really a helpful 24-page reference that you can go back and say, I just can't remember how in the world you calculate an AFES for a specific access category. So you can go back and just kind of look at the formula and look at the table, and it's really easy to do. So just as quick rehash, the mechanisms for channel access, you have carrier sense, you have interframe spacing, you have a contention window and random back-off timer, and then you also have slot times. So that's the basic gist of the paper. Those are the main topics that I addressed in it, looking at the different mechanisms, looking at the MAC architecture for 802.11 arbitration, looking at even just some of the reasons why it's even valuable to know this stuff, as well as several graphics to help you understand how it works, how the different pieces interact, how access categories work, how they relate to interframe spaces, and basically just went into detail, into technical detail about all of these things. So that's what the paper is all about. And I actually haven't had time to do it just yet, but I'm actually planning another iteration of the paper, just an update with mesh networking included, just to briefly explain that mesh also adds another channel access method they call it MCF, mesh coordination function. And mesh coordination function is actually pretty similar to HCF, hybrid coordination function, where it has both a contention-based and a contention-free channel access method. So the contention-based access method with MCF is EDCA. It's the same as with HCF. It adds a new contention-free method called MCCA. So that's MCF channel coordination access. And MCCA uses opportunity reservations, which is basically just a way to create a pre-established time slot for uncontended access to the wireless medium between mesh nodes. And that's called an MCCA opportunity, which with HCF, they call it a transmit opportunity or a TICSOP. MCCA, they're calling it an MCCA opportunity.
I have a question for you there, Marcus, on that one.
Yeah, sure.
What do you think the chances are that this contention-free is going to win? Contention-free never won in PCF, never came out in QoS, and now they're going to throw it out at mesh, and you think it's got a chance?
I don't think it will. I think there's slightly greater likelihood that it'll be deployed because it's between APs, so it might be a little bit easier to coordinate, but and it's backhaul oriented, I think. But I don't think it's going to ever see the light of day. It'll be just like the other ones.
Well, I appreciate your time today. This has been a great overview. I highly recommend anyone who's interested to go and look at the white paper. You can see a link for it in the show notes. Also, another just a kind of sidelight question for you, Marcus. Before you sat through GT Hill's class and were thinking about this, compared to after you sat through the class and you wrote this paper, I'd just like your a quick reaction on how you thought it worked before, and then after you know how it actually works, if that changed how you might design your wireless LANs.
Yeah, that's a great question. I think the biggest difference for me before was I sort of understood all of these little mechanisms. I understood sort of generically. I understood how carrier sense worked. That there was a physical detection and a virtual detection. I understood slot times, kind of. So I think I just had a far more cursory understanding of how it worked. Now that I know how it works, I'm not sure that my design approach would be so much different. It's just that I would be so much more confident in making changes in my configurations, especially if I was supporting QoS. Understanding the EDCA parameter set, so the AFEs and some of those issues, the contention window sizes, understanding how those things work, how they relate to QoS, I would have so much more confidence going into it and making a configuration change on my AP based on those factors. So I can't say that I understood well enough beforehand to design it a whole lot differently, but I would have a lot more confidence in my design.
One of the things that I've learned through this, learning more about the arbitration process, is you really want to keep your voice away from your data, because in the wired world, your QoS can have an absolute priority that it will always win. Here, the best we can hope for is a statistical probability, meaning every now and then a data frame is going to get stuck in front of a voice frame.
Yeah, that's a great point. And even one of the great things, that's a great point. One of the things that I should probably make a note to myself even now is when I do expand the paper a little bit, is talking about some of the shortcomings of 802.11 arbitration, and the fact that there are a lot of proprietary mechanisms out there where people are trying to control the medium much better with back-end queuing and scheduling before it even hits 802.11 arbitration, so that they're sort of controlling, and this is easier to do on a downlink than it is on an uplink, but that's a great point, Keith.
Yeah, and one other little piece on the same arbitration is it's given me a much greater understanding of the term contention domain. In the wired world, when we had hubs, we had collision domains. Here we have a contention domain, and any device which can hear is within range of another device. All of these mechanisms take over and take place, meaning if I can hear you, I'm going to stop and wait and play nice with you, but that means we're sharing the medium and we're cutting down our throughput. It's one of those things that a lot of designers go after, we need to get DB delivered everywhere. I'm more worried about making sure our contention windows are small enough to give us the throughput that we're after.
Yeah, that's a great point.
So thanks for your time. It's been a great little conversation, and I recommend everyone go out and read some other blog entries from Marcus on the CWNP website. Thank you very much.
Thanks, Keith.
Interesting facts, little-known tidbits, things you might not have known. Short little bits to set your mind a-reeling.
Yes, about nearly 2 years ago this week, I got talking to somebody in the Irish Railroad Service about the fact that there was no public Wi-Fi system on any of the trains in Ireland. Most of the public rail systems in Europe offer Wi-Fi access in some form or another. Similar to some of the services in the US. The Irish Railroad Services had actually, in the FAQ on their website, had a statement that they didn't offer Wi-Fi access because it was an outdated technology, and they would rather wait for a replacement technology before they would provide any kind of service. So at that time, I ended up on national radio with their PR spokesperson who at the time said that they didn't want to do it. It was too expensive. They didn't have the knowledge, etc., etc. But after a bit of pushing, it came out that actually his problem was it was too expensive. So I turned around to him and said, "Listen, how about this? We'll provide the service on your trains if you let us manage it and completely control the service in-house. We will provide the service at no charge to the Irish Railroad Service." And now, seeing that went out on national radio, he couldn't really back out anymore. So we had a meeting afterwards and discussed the way we wanted to do it and discussed what they would want out of it. But again, being a kind of a state-owned body, it took me nearly 2 years of pushing and prodding and repeated phone calls and emails and talks to the press, etc. Before, about 6 weeks ago, they approached us and said, "Okay, we give in. We want you to do a 6-month trial on the Dublin to Cork Railroad route in Ireland, which is the busiest one. So that has the highest traveller density. They want us to install Wi-Fi service on the train, run it for 6 months, and based on the results of that, they will then make the decision whether or not to let us roll it out across the whole fleet, site servers and installing equipment. But yeah, it looks very good."
Elevator speech. Our guests have just 2 minutes to tell us all about their product or service offering. Ready, set, go.
Hi, it's Joel Barrett here, and I work for Cisco Systems in our Advanced Services group. I'm actually a team member on the worldwide wireless practice. And the thing that Advanced Services does for Cisco is that we provide very high-level consulting services for our Tier 1 or Tier 2 customers. And what that means is that basically we're going into very established customer locations, even their headquarters, and providing consulting services, also integrating those consulting services inside Cisco. So, for example, where you might open a TAC case to Cisco, we can not only open a TAC case, but we also interact directly with the very senior level engineers inside TAC to understand exactly what the best practices are for a specific version of code before you even think about installing it. So if you're interested in getting information on Cisco Advanced Services, just check out cisco.com and type in Advanced Services.
Things every wireless LAN professional needs to know. Gear up, buckle down, and stand by for the real techie stuff.
Hello, this is Keith Parsons, and today's guest is Adam Conway, VP of Product Management with Aerohive Networks, and he'll be talking to us about wireless LAN control architectures. Go ahead, Adam.
Thanks, Keith. In networking, there is something called the data management and control planes, and this is an often misunderstood topic, and we're going to talk about this in the context of wireless networks. In a wireless network, there's been a lot of activity in the recent years about changing control architectures, changing data architectures, changing management architectures, and this has left a lot of confusion on what these actually are and what they actually deliver, and what's the benefits of the different ways of laying out these architectures. To get started, I want to give a little bit of background on what these different what these different systems are, what management plane is, what the control plane is, and what the data plane is. So starting off with the simplest, we'll talk about the management plane. In a networking system, the management plane is essentially, of course, how you configure, monitor, and manage equipment over time. And this is, in the networking industry, this is often described as something as simple as a telnet interface into a device, up to the most sophisticated policy-based management systems, which should probably be a centralized management system. In general, there are three different types of management systems out there. There's the simplest of which is called an element manager. An element manager is just what it is. It gives you a way of configuring one device. The next step up from that is something called a template-based management system, which of course gives you the ability to templatize those elements and manage multiple devices with similar configurations. And finally, there's a policy-based management, which describes the interaction between multiple devices. So, for example, if you have two firewalls and you want to allow a connection between both from a client to an application through both of those firewalls, a policy-based management system would allow you to set up one policy, which would allow that to go across, allow the rule on both of those firewalls. Now, that policy-based management is different than what people consider to be policy. So it's important to understand that distinction. Policy can be as simple as just one rule. Policy-based management describes the interaction between multiple devices to enable for example, a client to get to an application or connect two locations together or whatever that happens to be. And so in a nutshell, the management plane is something which is outside of the day-to-day function of a device. So, for example, a router or a switch, it would pass traffic and it can do all of its functions without the management plane being involved. But when you want to change the configuration, when you want to monitor it, when you want to see the status of the device, that's really where the management plane comes in. In correctly designed systems, if your management system fails or your management system is unavailable, it usually has no impact on the network functionality. It can still function fully. So that's essentially the management plane in a nutshell, and a description of the different ways of delivering management. So the second I want to talk about is the data plane, and this is the component that you deal with as a network engineer most frequently. This is basically, in its most simple sense, about getting packets from one interface to another. So in a router, as an example, it's about getting it's about taking traffic in one Ethernet port and out a T1 port, or in a switch, as simple as just getting a packet or a frame from one port to another. In wireless, it's the same. It's about getting things from a wireless interface to an Ethernet interface. And this can also be from virtual interfaces in some implementations as well. So it doesn't necessarily need to be a physical interface. So it can be things like a management interface or a loopback interface or a VLAN or two different VLANs on the same port. So data plane is about getting packets from one place to the other. What's most interesting about the data plane, though, is what happens as that data goes from one port to another. In the simplest form, the device just makes a decision. Based on the packet type, or based upon the header, or based upon whatever, I'm going to send this packet to another interface. But it can be more than that. It can you can apply a firewall rule, which basically says that these certain ports should behave. We should do this. We should check the packet based upon these rules, or you can apply an action to it. For example, I'm going to queue the frames queue the packets or frames in this from this interface in this way, or I'm going to NAT these frames to do an address translation. So the data plane actually does a lot of the heavy lifting of the device, and in general, the reason you buy a big processor for your networking gear, or the next reason you buy the next generation networking gear, is because the data plane is also the most taxing on the system. So, when you look at a device and you want to determine how big it is, you often say, how many megabits, gigabits, or tens of gigabits do I want through this device? So that's the data plane that you're talking about. In modern networks, the part that makes a lot of the networks work is not just the data plane and management plane, it's the control plane. And the control plane is probably the least understood and the most complex, most nebulous of the three. And there's lots of definitions out there, but I think the best definition for control plane is that it describes the interaction between networking devices. So different from management plane, where you have a manager talking to devices, or a console talking to a device. This is instead two networking devices talking to each other. This control plane is often mission critical to delivering the networking service, and basically shares information to enable uptime, to enable updates of information about the network, communicate congestion, those sorts of things. The ultimate classic example of a control plane function is a dynamic routing protocol. And that's, of course, a well-defined protocol between two routers, and they communicate and provide that information. But there's other examples of this as well. There's spanning tree. There's something that I would consider part of the control plane as well, things like VRRP or other resiliency capabilities that basically describe a protocol which enables these devices to work together to guarantee uptime, to guarantee maximum performance, and those sorts of things. In wireless, the control plane is very sophisticated, and this has been why there's been so many discussions about controllers and lack of controllers and those sorts of things. So control is actually one of the most interesting topics in wireless, and has not been as well defined as it is in routers or switches. So that gives kind of a nice introduction to what those three different planes are and how they're defined. The next topic is then describing how this has been applied in wireless. So when wireless was first, when 802.11 was first ratified, and the first access points were delivered, they were essentially standalone devices. They basically had no control plane. They would either manage them via CLI. They would basically take a packet off the air and stick it on the Ethernet, or vice versa, and that's essentially all it would do. It was essentially a simple bridge between those two networks. Now, as time went on and you start adding more access points to a network, you start to be more concerned about having, how you handle roaming is probably the biggest example, and then also. As it happened with the first devices, the management plan was kind of underdeveloped, and there wasn't very many applications that effectively managed lots of these access points. So the industry, took a look at multiple different ways of solving this. The first couple ways were probably misguided and didn't really work. The first was a standard called IAPP, which essentially described how APs can talk to each other to enable a few functions. The second was a architecture delivered by Cisco called SWAN, which involved a bunch of different functions, a bunch of different devices talking together to enable things like roaming and RF control. That also didn't work and was basically eliminated after Cisco acquired Airspace, which is a controller vendor, which was the third way that people tried to handle this. Basically what a controller did is it took the control plane and it centralized it, and it said there's one device which will describe all the interactions between these devices, and the two biggest capabilities of this were roaming, or basically mobility, as well as RF control. So this is saying this radio should be on this channel at this power level, and we're going to do this to minimize interference. We're also going to load balance these clients across these different devices, and they made all those decisions centrally in a single central device, and that enabled this control plane to actually really come to life in Wi-Fi. If you look at pre-controller Wi-Fi solutions, what are often called autonomous access points, they did not, like I said, the control plane never became fully developed. And in controllers, this was the first time this really happened. Now, controllers are more complex than that, though. They didn't just solve the control problem. They also did two other things. One is that they instantiated the data plane in the controller as well. So a packet would actually come in across the air into an access point. The access point would forward that data to a tunnel, or forward that packet to a tunnel. That tunnel would go to the controller, and the controller would forward that packet again. So you basically forward the packet twice. But in 2002, when controllers first came out, that made an awful lot of sense because you couldn't do firewall on an access point. There wasn't enough processing power on the access point. And there wasn't enough processing power to do quality of service in an access point. And therefore, you put a piece of big iron in your closet, which would do that for you. And that we could sell cheap access points and expensive controllers and deliver an entire solution that could provide the functionality that you wanted, and was able to deliver this control plane and data plane with for an additional cost, and that additional cost was the cost of that controller. So essentially now you have access points plus controllers. Controllers also, and this is where it gets a little confusing, controllers also did part of the management plane too. So this controller became data management and control for all of these access points connected to it. And to make it more confusing, a lot of those controller vendors also provide a separate management console, which also just does pure management plane. And it's important to clarify all these points because as you look at the traditional three-layer model or three-plane model of data control and management, the controller is a unique beast in the networking world because there's no equivalent for example, in routers or switches. So that was what I would consider to be the third solution for this architecture. What Aerohive has delivered, and I believe, and actually we're seeing evidence that many of the other Wi-Fi vendors are going to be adopting this approach as well, is that control can be distributed, and this is not a unique or novel approach. In fact, in all other networking devices, control is distributed. So, for example, in routers, you would never think of managing static routes centrally any longer. You would always use a distributed or dynamic routing protocol. In spanning tree, the same thing. You would never consider centrally managing loops and those sorts of things, even though in the initial world, in the initial LAN deployments, there were things like switch virtual circuits that were all centrally managed. We would never think of that today. We would use spanning tree. Protocols like DRRP are standardized, and those are all, again, expected, are distributed capabilities that they don't require a controller, so to speak. In wireless, this move from centralized control to distributed control is inevitable. And Aerohive, we've been doing this for a couple of years, so it makes us an expert in it. But we also certainly understand, and it's certainly an open secret that all the major vendors in the market are looking at this and looking at how to distribute control, eliminate the controller, because essentially that's the best approach to go to enable things like scalability, resiliency, and basically eliminate the cost of that controller out of the network. And if you go back to things like routers and switches, the reason dynamic routing was put in place in the first place was for just those things: performance, scalability, reliability, and it's the same thing for access points. It's no different. Now, the thing that is different about access points is that the data shared is certainly not the same. Now, in an access point, the control plane can be made up of multiple things, and that's things like roaming. So as a person moves from an access point to an access point, you need to keep track of their credentials, who they are, maybe their PMK, which provides the ability for fast roaming in 802.1x. You may need to keep the policy associated with them. There's a variety of information surrounding an individual user that needs to be in place for mobility to work. And the reason this is unique to wireless is that in routing, you don't migrate from one interface to another in a seamless fashion. And you'd have to unplug and replug in, which would usually cause policy to be reapplied. That does not exist in wireless. You're expected to seamlessly roam between devices. The second is RF control, and I mentioned this previously. So things like power channel, load balancing, a variety of other functions as well. And then there's, of course, other areas of control plane as well. In meshes, you have to deal with stuff like routing as well, more layer 2 routing in most cases. But if you have a mesh, that's certainly a routed network, and you need to offer that. Actually, I take that back. Not all meshes are routed. Some are flat networks, in which case you would use a spanning tree. So but that again is a control plane function. So there's a variety of control plane functions that need to be applied, and it makes it a little bit more challenging than it's been in the router, than it has been in routers and switches to offer a distributed control plane for wireless. However, we're now at a point in the industry where it's clear that that's important. And the reasons for that is that the network has changed and the usage of the network has changed. .11n is a step function in Wi-Fi. It provides better resiliency, provides much better performance, and it's a much better protocol in that it enables and standardizes things like aggregation and other functions in Wi-Fi, and really gives a roadmap to get much better performance in the future as well, with things like 3 and 4 spatial streams going forward. Now, what that has enabled is Wi-Fi to become a primary network, not necessarily the only network, but certainly a primary network where a user can be online all day and never be plugged in. And in fact, all the users in an office space can be in that mode, and you would have enough bandwidth, enough capacity to enable that. Now, that is a big difference from what people expected out of ABG. Certainly you could do that, but at a more diminished performance. And in general, ABG networks, with exceptions of places like retail and hospitals and things like that, were used for more convenience networks. Now, this migration to 11n also needs an architecture that enables the resiliency, the wired-like performance that you would expect out of the network, and that's why everybody's relooking at their architectures. So, as you look at, going back to the concept of a controller, looking at the centralized control model, as I said, as something which all networking technologies have started with, routing with centrally managed static routes, switches with things like switch virtual circuits, and those legacy capabilities have all moved to distributed. Wi-Fi really needs to have the same thing happen. And if you look at a controller, and the reason for this would be that if you look at a controller, certainly it could be a bottleneck. Some networks it's not, some networks it is. It certainly can be a single point of failure. Most notably, it can be expensive. Access points now have enough horsepower in them to run all these functions on their own. They certainly don't need a controller because of processor pricing, but they do need a controller. They wouldn't need a controller for any of those reasons, and essentially you can eliminate the cost, the resiliency issues, and the complexity by moving to a more distributed approach. And like I said, that's why most of the industry is moving in this direction. So going forward, what does this mean for us? As an industry, Wi-Fi is still fairly, is still fairly early on compared to routing and switching. Those are there's 10 or 15 years older technologies. It's a very exciting time to be in wireless. People are deploying wireless to much greater extent. There's been huge advancements in wireless, things like 11N and new ways of managing and controlling them. And this is really what enables the wireless network to become the primary network. In that happening, in the move to wireless becoming the primary network, you will see most, if not all, vendors starting to adopt a more distributed approach to networking. Some vendors have already done this with their data plane. You will see in 2010, you're going to see major vendors, eliminating the need for their controllers and moving more towards a distributed approach across the board. Some of them will be half steps, some of them will be full steps in that direction, and it makes this time for Wi-Fi very, very interesting. Only recommendation I would have before buying a new Wi-Fi solution in 2010 is make sure you ask your vendor if the controller is the right thing to buy, or whether they're going to adopt a controller-less solution in the near term. It can save you a lot of money, enable you to buy more access points, and get more capacity and coverage in the short term. So that concludes this conversation about data control planes, data control and management planes, and how it applies to wireless. I also talked a little bit about where wireless is going, and thank you very much, Keith.
All right, thank you, Adam. That was good. I appreciate your time and your obvious expertise in this field. Thank you very much, Adam, and we'll see you in the next episode. Thanks. Well, another show has come and gone. I'd like to thank those who have helped out: Joel Barrett, Marcus Burton, Avert Bopp, and of course Adam Conway from his last segment we just finished. For those of you who'd like to also contribute, feel free to send a message to feedback@wirelesslandprofessionals.com. If you have any questions, ideas, or things that you might like to see on the show, feel free to either leave us a voicemail on the feedback line or just send us email. Thanks again. See you next week.
Wireless LAN Weekly, a podcast focused on the needs of wireless LAN professionals. We look forward to your feedback. Please leave your comments at the bottom of the show notes, or email feedback on the show can be sent to feedback@wirelesslandprofessionals.com. If you'd like to leave a voicemail feedback, just call 24/7 and leave a message at 1-801-481-9018. Until next time, this has been another production of wirelesslandprofessionals.com, a place to educate, inform, entertain, and inspire.